All right, this is the solution guide for the mole-to-mole stoichiometric practice sheet. I'll work through these problems so you can see how they work. First thing you have to be aware of in order to in order to solve any stoich problem, you have to start with a balanced formula equation. Let's take a look at this. I'm going to leave the iron alone for now because I have iron all by itself. That's going to be pretty easy to fix. Let's look at a 4 oxygen and 1. So if I go ahead and flop a 4 here, that gives me 4 oxygen. The hydrogen turned into 8. I can fix that by putting a 4 here. Now everything is fixed minus the iron. So if I put a 3 here, it's good. It's balanced. That is the balanced formula equation 1, 4, 3, 4 for the coefficients. Like I mentioned to you yesterday, those coefficients are actually moles, right? And that's going to help us solve this. So looking at this is how many moles of pure iron would you obtain if I had 1.96 moles of, that's not iron 4. I don't know what that would be. But anyway, it reacts completely following to the following equation above. So let's see. Let's start off with what we know. 1.96 moles Fe3O4. Now, if we're trying to go from here to iron, you're going to notice that the ratios for every 1 you get 3. Since I want to get rid of moles of Fe3O4, they need to go on bottom. Well, how many? Well, there's 1 here. So I'm going to put the 1 mole Fe3O4, and according to our balanced formula, for every 1 mole, it produces 3 moles of iron. Moles cancel. I'm ready to solve, so all I need to do is grab my magic box, 1.96 times 3. It's going to have 3 sig figs because of those 3, and so it's going to be 5.88 moles of iron. Okay, next problem had the exact same formula, so I can go ahead and just put the coefficients here. We didn't have to balance anything again. Okay, so I want to know how many moles of hydrogen are needed to completely react with 2.25 moles. So I'm going to start once again with what I know. 2.25 moles Fe3O4. And this time I'm comparing that to hydrogen, like I've mentioned before. It doesn't have to be a reactant related to a product. You can have two reactants related, 2 products related, a product and a product, a product and a reactant. I mean, the combinations are, any of them. Okay, so let's take a look here. According to the balanced formula, once again, I have 1 mole Fe3O4. Let me take care of those stray marks. Okay, and then it says how many moles of hydrogen? Well, according to my balanced formula, there are 4 moles of hydrogen. Moles cancel. I'm ready to solve. I'm going to take 2.25 times 4. When I do that, and you have to have 3 sig figs, so you have to write it as 9.00, even though that comes out as exactly 9. You have to write 9.00 because of significant figures, 9.00 moles of hydrogen. Next one, we have a new formula, so we have to do some new balancing. Let's leave the aluminum alone because it's all by its lonesome. Oxygen, I have 2 and I have 3. Common factor is going to be 6. If I flop a 3 here and a 2 here, I have 6 oxygens on both sides. My aluminum over here becomes 4. I flop a 4 in front of there. Don't get all bent out of shape by the S and the G. Those are just states of matter. All right. So I want to know how many moles of aluminum are needed to react completely with 3.33 moles of oxygen. Start off with what I know. 3.33 moles of oxygen. And I'm comparing oxygen to aluminum. Well, according to my balanced formula, for every 3 moles of oxygen, there are 4 moles of aluminum. Moles cancel. I'm going to take 3.33 times 4 divided by 3. When I do so, I need 3 sig figs in my answer. It's going to be 4.44 moles of aluminum. Next one, same formula, so we're going to go, this was 4, this was 3, and this was 2. I want to know how many moles are produced from 5.25 moles of aluminum. So start out with what I know. 5.25 moles of aluminum. And according to this, for every 4, I produce 2. Okay. So for the moles of aluminum to cancel, they need to go on bottom. There are 4 of them. For every 4 moles of aluminum, there are 2 moles of aluminum oxide that are produced. Moles cancel. 5.25 times 2 divided by 4. When I do so, your calculator spits out 2.625. You need 3 sig figs, so it's going to be 2.63 moles of aluminum oxide. Okay, this last one, this is a little different. Okay, so it wants to know how many grams of aluminum oxide do you get in your answer for number 4. Okay, so what you could do, and what I would probably, we haven't done the mole to mass conversions yet, but guess what? The previous problem, we knew there were 2.63 moles of aluminum oxide. And guess what we were doing last week? We were converting moles to grams, weren't we? And so you already actually know how to do this. All we have to do is come up with the molar mass. Okay, so we have to add these up. Let's see. So we have a total of 2 aluminums. And each one of these aluminums weigh 26.98. Okay, and it looks like 3 oxygens each at 16. So if I sum those, it appears the molar mass of this compound is 101.96 grams per mole. Okay, so just like what we did last week, moles go on the bottom. How many? 1 mole. How many grams is that? 101.96 grams. Moles cancel. 2.63 times 101.96. You're going to have 3 sig figs because that's what you had to start with. The answer, 268 grams of aluminum oxide. And so that's how you solve those problems. Not too bad. I encourage you guys to make certain you do it just as I have done it, where you put units and labels throughout the problem, observe sig figs, and that's it.